we are going to talk about part 2C2, the chemical and biological synthesis of peptides. And here again is just sort of a quick outline of where we are on that roadmap. So last time we talked about protecting group strategies, and now we're going to talk about coupling agents. Okay, so what is a coupling agent? What do we mean when researcher says, oh, I need to use a coupling agent for peptide synthesis? So coupling agent really is a compound that will bring together, at least in our case, a carboxylic acid and an amine together to form that desired peptide or amide bond that we've been talking about. So here's your amide bond. So a coupling agent is a specific reagent or chemical that allows us to do that. Okay, so it brings a carboxylic acid and an amine to form an amide bond. Okay, so let's look at a classic coupling agent that is used, regularly for peptide amide bond synthesis. So this type of structure here is called a carbodiimide. So there's a carbon and it's a diimide group, and the name of this compound here is called dicyclohexylcarbodiimide, also known as DCC. So how is it that this is going to act as our coupling agent? But before we answer that, how does this specifically activate our acid? So recall our acid has very low energy, and we need to activate it in order for it to get higher in energy so it can overcome that activation barrier necessary to make that amide bond. So if you look at your carboxylic acid, we're going to first take the carboxylic acid and react it with this compound called DCC. I would like you to just think about for a few seconds in terms of what you think will happen when these two compounds come together. All right, so I want you to think back to acid-base chemistry in terms of what we were learning when we had an amine. So when you have a nitrogen with lone electrons, there was a big tendency for those electrons to just come and take off that proton. So the same thing is going to happen here. The nitrogen electrons on DCC are going to come, and you're going to remove that proton, and you're going to be left with now a carboxylate and a protonated form of DCC. Okay, so what we've done now is we've gone from something that is really not a good nucleophile or electrophile, but something here that is a poor electrophile, but is actually a good nucleophile. The electrons on that oxygen, it's very electron rich, so you now have a good nucleophile. On this compound here that I'm circling with my hand, do we have a good electrophilic site? Yeah, we absolutely do. This is a good electrophile. The electrophilic site, by activating one of those carbodiimides, you now have a positive nitrogen, meaning that electron density is moving in this direction. Okay, so our electrophilic portion here is this carbon that really would be happy to get attacked by a nucleophile. So what will happen is that you'll get attack at that central carbon, move electrons to the nitrogen to get rid of that positive charge. Once you have that, you now, let's draw what that covalent structure looks like. You now have a covalent bond between that oxygen and this carbon that we just reacted and formed to give this compound here. So we've gone from a carboxylate, or maybe we've gone from an acid to a carboxylate, so very, very poor electrophiles, to something that is now an ester, okay? And this is actually a very special type of ester because you now have these electrons here where they could come into this oxygen here and they could move electron density, reducing the electrophilicity. However, you do have strong resonance form moving in this direction here, meaning that this whole group here actually is quite a good leaving group. And therefore, what this does is that makes this carbon here very electrophilic. So we actually call this not just an ester, but an active ester. Okay, so very electrophilic form. So what we do here is once we incubate the DCC with the carboxylic acid, we wait about 30 minutes or so until that active ester is formed. And then what we do is we add the primary amine, and this will now come, and this will react at the electrophilic center, which is right here at that central carbon. So what this will look like now is you just draw in your connectivity. You have a tetrahedral intermediate. You still have that DCC portion attached. And what you can see here is now you have a negative oxygen, positive nitrogen because it now has 4 bonds. So what you're going to do now is you're going to take a very weak base. That weak base really could be another one of these DCC molecules or even this amine here. That will come and remove that proton. Okay, so now you have a neutral nitrogen. And as I mentioned before, this is actually a very good leaving group, okay? So once your tetrahedral intermediate collapses, the oxygen electrons come down, a new pi bond forms here, and then you're going to get proton transfer from the conjugate acid of that base that took that proton earlier to give you your desired amide bond. Okay, so we've used DCC as a coupling agent to make our desired amide bond. Okay, and our byproduct is this compound here, which has come off. So let's draw what that looks like. Okay, so this here actually is a byproduct. It precipitates out. We call this dicyclohexylurea. So urea actually looks like this. This is a biological byproduct. So this is very much like urea, except there's two cyclohexyl groups. So we call this dicyclohexylurea, or also known as DCU. Okay, this is a byproduct. Okay, but you're not so interested in that, because what you are interested in is the desired amide bond. All right, so that's how we activate our acid using DCC. So here's sort of a summary of that reaction. You can take a carboxylic acid with a primary amine using DCC to form the amide bond. This is your byproduct. And the nice thing about DCC is that it's actually relatively inexpensive. Okay, you can, researchers like it because it's fairly cheap, and your yields are actually around 80 to 90%, which actually sounds pretty good. But later on, I'll tell you that 80 to 90% yield maybe isn't that great when you're doing several amide bonds in a row. Okay, so DCC is one example of a coupling reagent. Other examples of good coupling agents or reagents include these 3 characters here. So, all right, so you've learned about DCC. I'm just going to redraw sort of that active intermediate form that we just looked at. Okay, so it looks like this. And then you would have your carboxylic acid come in here, and then this would come and this would react, right? We just learned that right now. So that's how DCC works. As I said, DCC 80 to 90% yields and fairly inexpensive. If you do have some more money available, you might be interested in something called HBTU, which stands for hexafluorophosphate. So there is hexafluorophosphate anion that is coordinated tetramethyluronium. Okay, so HBTU gets its acronym from this. And this is also a good coupling reagent. It's a little more expensive. Okay, I'll put $2 signs. But I want you to think of how that first activation step with a carboxylate reacts with HBTU. So look for the electrophilic site, right? Can you find the electrophilic site on this molecule? Well, look for something that's similar to what we learned just now, right? So you have a carbon here, double bonded nitrogen that's positive. So this is going to be your electrophilic site. All right, so that's HBTU. Why might you want to use HBTU? Well, you can typically get yields from around 95 to 98% yield. So it's a more effective coupling reagent. Okay, let's look at another coupling agent that's very similar. It's called HATU or HATU. And really the only difference between these two coupling agents is the presence of this nitrogen or the absence of that nitrogen in HBTU. So HATU is actually a more expensive reagent just because of that extra nitrogen. And it stands for hexafluorophosphate aza, which means nitrogen, benzotriazole, triazole, tetramethyluronium. Okay, again, if you think of how this will get activated, this will react here in an analogous way. And the yields for this one actually are even better, around 99%. So you get slightly better coupling efficiency. And you also have, of course, that hexafluorinated phosphorus group. The last one I want to talk to you about is something called PIBOP, which is an azobenzotriazole pyrrolidino phosphonium hexafluorophosphate. Okay, and this actually is going to function similarly to the other groups, and that you get now attack at the central phosphorus instead of carbon. It's in a very effective coupling reagent, 99.5% yields on average. But this one is actually quite expensive and requires typically deep pockets. So you can see here as you go from left to right, you increase the price, price goes up, but so does the coupling efficiency. So researchers will usually start with something like DCC, see how that goes. If they need higher yields or they're having a very sluggish coupling reaction, then they might go to something a little more expensive. All right, so let's go through an actual example here. Let's make a dipeptide. So I think we're ready to make some bonds. All right, so here is our desired compound. So the first thing that we want to do is we want to take this compound and we want to figure out where that amide bond is and how we're going to make it. So if you look at the structure here, it's a dipeptide. So let's first put a little dotted line on that amide bond, and then let's break it up into the two main constituents. So before that was an amide bond, it was an alanine, which is a carboxylic acid. And then on the other hand, what we had on the other side is this lysine molecule. Okay, so it used to be a free amine. So at the beginning, when you're trying to figure out how to put these two molecules together, what I recommend you do is I recommend that you put where you think the desired electrophile and the desired nucleophiles are, in addition to any undesired nucleophiles. So you can see here, let's start with the desired nucleophiles. So this nitrogen here wants to form the amide bond. So this is a desired nucleophile. And this needs to react here, and this is our desired electrophile. But as we know, this is a lousy electrophile. However, we need to take into account some undesired portions on this molecule. So here we have an undesired electrophile and nucleophile. In fact, we don't want this to react with anything. And this nitrogen here is an undesired nucleophile. Okay, so we want to put these together, and we need to now take, for example, this alanine here and protect the undesired nucleophile. So let's use F-MOC chloride, which we learned in protecting groups, and let's put on that protection of the nitrogen. And so now we have an F-MOC protected alanine. All right, so we've taken care of the undesired nucleophile on alanine. With the leucine part, we don't want to touch the amine part, but we need to protect the carboxylic acid. So what we're going to do is we're going to treat this with an alcohol, and we're going to use catalytic protons, and we're going to do something called Fischer esterification, which is a type of a esterification that you learned in second year organic chemistry. So what will happen is that you'll now have your desired amine untouched, and you'll have your alcohol now formed as an ester here. So that's now protected. So now what we're going to do is we're going to take these two molecules together, add DCC, or coupling reagent. You could add any of the other 4 coupling reagents, and what we're going to do is we are going to now put them together and make our dipeptide. Okay, so we've made our desired peptide. There's our desired amide bond. And then the last thing we need to do now is remove those protecting groups. So we have to remove the F-MOC. I'll teach you how to do that soon. We're going to use a base. It's actually called piperidine. And that takes care of that. And the other thing we need to do is take care of that ester. So if this ester is like a tert-butyl group, then we can use some kind of acid to remove that group as a tertiary carbocation. And again, as I mentioned, we will talk and learn more about that later on. So that's how you make your desired dipeptide. Just going to bring that up so you can see all those functional groups. Okay, so let's, all right, so now we know how to make these amide bonds. Let's, I'm just going to tell you a little bit about some, nothing's perfect, so things don't always go as planned, and I want to just bring you aware of some unwanted side reactions that can occur during peptide synthesis. So one of the things that can happen is that you can get something called oxygen to nitrogen acyl migration. Okay, what is that? So so here's an example of an active ester. Okay, this is a Bach protected amine, carboxylic acid reacted with the carbodiimide. Okay, so this is exactly what sort of the DCC would look like after it reacts with the carboxylate. So we've already established that this carbon right here is an excellent electrophile, right, from this active ester. Excellent. Okay, so when you're doing this reaction, okay, so during active ester formation with DCC, the carboxylic acid reacts exclusively with DCC. Okay, it's important that you just react these two together, followed later, okay, so around 30 minutes, by the addition of the amine. Okay, so once this oacyl isourea is made, it's important that you add the amine almost immediately. So the reason is that if we wait too long, one of the consequences is that you have these nitrogen electrons here. And what could happen is that this thing gets a little bit impatient because it's such a good electrophile. So you could actually start getting intramolecular attack from the nitrogen from the carbodiimide onto that electrophile. And if that were to happen, what you're going to end up with is you're going to have a 1, 2, 3, 4-membered ring intermediate. That is, not the best looking structure. You've learned that 4-membered rings are not that favorable in organic chemistry, and that rule still holds true. So what's going to happen is that this ring is going to want to break, but instead of this carbon-nitrogen bond breaking, you're going to move electron density to this portion of the ring and move electrons up into the nitrogen this way. So if that happens, you're going to now end up with this compound here, which actually is now not an active ester. Okay, not an active ester. It's not reactive anymore. You have 2 amides here. Okay, so basically the reactivity is short-lived is what I'm trying to say. So it's important that you add these things in a timely manner. So therefore, so this is called O to N acyl migration. Therefore, it is important to add the amine immediately once the O-acyl isourea compound is made. Okay. All right, so that's just something that researchers need to keep in mind when they're doing this chemistry. Another consequence of this reaction is you can get unwanted side reactions during the peptide synthesis. All right, so let's, okay, so again, let's take a look at a scenario where you have this compound and you could actually lose your stereocenter. All right, so I'm going to draw this in a slightly different orientation. Okay, so we're going to draw this like this. Okay, and what is going to happen is that you're going to actually get the Bach group, which is a protecting group. And, you know, this is actually unintended, but unfortunately what could happen is that you could actually get the oxygen now reacting here and forming a 1, 2, 3, 4, 5 membered ring. Okay, so here you have this oacyl intermediate that has self-reacted with itself. And then you can now have a base come in to remove that positive charge off of that oxygen. And then what's going to happen here is you're going to have this compound that's going to look like this. Okay, so at this stage here, we're going to have the oxygen electrons come down, and we're going to remove off our oacyl urea group to reform this ketone. Keep in mind, I still have the same stereochemistry at this position. Okay, so I have this stereochemistry at this position. However, if you let this sit around too long, what will happen is that you'll actually end up with a racemic mixture at that position. Okay, so one of the consequences is you've now gone from something that has stereospecificity to something that loses stereospecificity. So why is that? How does that happen? And remember, we have a weak base around. So I want to bring your attention to this proton here. Okay, so this proton here, if we remove it, we actually can form this compound here that looks like this. And this compound here, actually, if you look at it, what is special about this compound? This compound has 2 pi electrons, 1, 2, 3, 4, and it also has electrons on the oxygen. Okay, so it has what is known as 4n plus 2 electrons. So that's, in this case, n is equal to 1, 6 electrons. This is an aromatic species. So we've gone from something that is not aromatic to something that is now aromatic. Aromatic compounds are quite stable, and this is the driving force to remove this proton. Turns out that the pKa of this proton is around 10, which is quite low. So once you lose that proton, you lose stereochemistry because you now have an sp2 carbon. In order to pick up a proton back, you take the conjugate acid and then you pick up the proton. But because this group here is sp2 and is planar, when you pick up the proton, it can be picked up from above or below. So it can be picked up, imagine here, this is your plane. When it picks up the proton, it could pick it up on top, or it could pick it up from the bottom. So the net effect is you could get loss of stereochemistry. How do you avoid that? Well, you can see the Bach group kind of participated in that. But again, if you wait too long after that oacyl isourea intermediate is made, then that runs into some problems. So you want to add the amine as soon as possible so you really don't get this side reaction occurring at the bottom. Finally, some other consequences of peptide synthesis. So when we are making our peptide, we need to think about which way we're going to make the peptide. So here you have an N terminus, here you have a C terminus, and a couple different scenarios you can think about. You could have a scenario where you have an N-protected amino acid here, and this is going to react with a growing peptide. So you're going to grow it, adding to the C terminus. And we've already learned that, well, you could get a scenario here where the oxygens could come here and maybe start ruining the reagent a little bit. Or you have the other system where you're going on the N-terminus where you have the amine that will react at this carbon here, but one of the consequences is that this could also self-react. So what is better? Is it better to ruin the reagent or better to ruin the peptide? Think about that for a few seconds and I'll let you know what the answer is. It's best to add excess reagent, and lose 10 to 20% of the reagent for each coupling, as opposed to ruining your peptide for each coupling. That peptide you're making is quite precious, right? As soon as you start growing that peptide, you really want to minimize any destruction to that peptide. So we don't add things in the C-terminal direction, we add it in the N-terminal direction. Okay, so it's better to do that as opposed to ruining your peptide for each coupling. All right, so let's look at another example here. We're going to look at a protein called isopenicillin N. In order to study this enzyme, we need to synthesize a tripeptide. Okay, so this tripeptide, looks like this here. Okay, and we need to figure out how we're going to make this tripeptide here in order to study this enzyme. All right, so this is where chemical synthesis of peptides becomes really important. So let's take a close look at this peptide. And as you can see here, this peptide I've kind of color coded a little bit. Here's your desired peptide. First thing you want to do is look for those amide bonds. So you can see here you have an amide bond right here, and then you have another amide bond right here. So let's break that up into the starting material units. Okay, so in red, you have your carboxylic acid. In black here, you have your cysteine. And then in blue, you have your valine. Okay, so I'm just kind of filling in what those would actually look like. What I have in star are the groups that have to be protected. And then what I have in a dark triangle here is the groups, the carboxylic acid groups that have to be activated. Okay, so now that we understand that, we need to protect and do some protection of these groups. So we need to protect carboxylic acid of the valine. So a good way to do that is through Fescher esterification. So we can take like a benzyl alcohol and add catalytic protons. To generate an ester, a benzyl ester. We also need to think of that thiol group on that compound. There is a cysteine present, and we haven't talked about how to protect that. A good way to protect that is to treat this with something called benzyl chloride, abbreviated BNCl. And benzyl chloride is great for cysteine because you can get simple SN2 reaction occurring here. So now you have a protected form of that thiol. So both the amino group and the carboxylate cysteine need to couple to one another, but we can't react all three peptides at once. We have to do it stepwise. We can't put everything together in one pot. So this is where we take our cysteine that has a protecting group here, and we're going to now protect the nitrogen with our good friend Bach anhydride. Okay. So we take Bach anhydride, we react that. This thing is doubly protected because your cysteine is protected, and this is abbreviated as such. Bach group, benzyl group, free carboxylic acid that needs to be activated. Now that we have our protected amino acids, we need to activate the carboxylic acid towards coupling. So now we take our carboxylic acid and we treat that with coupling agent. And we've already learned good coupling agents in this lecture. So let's use DCC, okay, our coupling reagent. So we'll add DCC, and then we'll add our primary amine. Okay, and this will form our desired amide bond. Okay, so we're taking these two groups I'm highlighting in red, getting them to couple with each other. All right, so now we need to remove the Bach group. So I've just redrawn that structure here. So a good way to remove the Bach group is with acid. And we can use trifluoroacetic acid, 2.5%, trisopropylsilane, 2.5% H2O. So what that will do is that will remove that Bach group. Your benzyl group is still on. And then what we're going to do now is we're going to get this amine here, and it needs to react with this group here. Okay, so we're going to put these two together, add DCC to activate the carboxylic acid, and then we need to remove the benzyl group. We're going to use H2 over PDC, hydrogenation. You've seen this before. And then number 3, you need an acid to remove the last Bach. And ester. Okay, where was that last ester group and Bach? So before we actually took this adipic acid, this was free, and then we can imagine protecting the amine group with Bach and hydride, and then with an alcohol, one equivalent with catalytic acid to protect this group here. Okay, so once you do this together, you use acid, and then you generate your tripeptide. All right, so the other thing you can do too is you can use FMOC as a protecting group for synthesis. So we use Bach in that case. So what I'd like you to try on your own is to use FMOC as a protecting group and think of the reagents and things you would need to do that. Okay. The last things I just want to touch a base upon are is the deprotection of FMOC. Okay, so typical. So the way that FMOC is deprotected is actually a little unusual, but it actually makes sense. You take something called piperidine, which is a base, and this base actually is going to remove this proton here, and you're going to get elimination. Like this. And if you follow the arrows, you're going to form this compound here, plus carbon dioxide, plus your desired deprotected amine. Okay, so you actually use 20% piperidine. Okay, 20. It's not a full piperidine solution. 20% piperidine is enough to do this. Now, why does this? This is an sp3 CH bond. Why does that become deprotected with piperidine? Because typically, these bonds have a pK that are quite high, 45 to 50, all right? And you wouldn't think that piperidine would be able to do that. The reason is that once you remove this proton here, you form this stable compound, which is sp2, and now adds conjugation to this compound. So this conjugation electronic is actually quite stable. This is a stable byproduct. So what happens is that this actually has, instead of a pK of 45 to 50, it's actually considerably lower, pK of around 25. Okay, and the byproduct of FMOC deprotection is a highly conjugated and stable molecule. Here's just some other amino acids that have other protecting groups on them that we need to keep in mind. So, or other functional groups that we need to keep in mind. This is aspartic acid. So aspartic acid, you know, if you want to use this for amide bond coupling, you need to protect the amine with Bach and hydride. But you also need to protect the side chain carboxylic acid, right? This is your desired carboxylic acid. This is the undesired one. So we need to find a way to protect that. So a good way to do that is to use something like one equivalent of like a phenyl alcohol to protect and then once you use one equivalent, if you get a mixture of different compounds, you can actually separate them on a column chromatography, and this could be your desired compound that's now ready for activation. Serine and threonine, what do these look like? So these have side chains with an alcohol group, and so we need to protect the nitrogen. We also need to protect this alcohol here. So a good way to do that is to use a silyl protecting group. Silicon loves oxygen or electronegative substituents. So if we treat this compound with the silicon protecting group, this group is actually called tert butyl dimethyl silyl chloride, also known as TBDMS, tert-butyl dimethyl silyl chloride, also abbreviated as TBS chloride. So TBS, so I guess people got sick of writing all these letters, so TBS chloride is also another widely accepted name. So you can protect that alcohol group with TBS and then protect the amine with Bach and hydride. And you now have Bach. Okay, so these are just some common examples. And then this last slide here is, I just want to talk about lysine a little bit. Lysine is an amino acid that has a amine as a side chain. So we need to think about this amine whenever we're using this for peptide bond synthesis. If we use two equivalents of Bach and hydride, we will end up protecting both of those nitrogens. Okay, and this can be a very useful strategy for peptide synthesis. However, if you need to keep building the chain off of this and remove the Bach group, if you remove the Bach group, then you're also going to remove this one, and then you'll start branching off a peptide. And therefore, this strategy will only work if lysine is the last amino acid to be coupled. Okay, so if we want to protect lysine in a way that allows this to be completely protected while being deprotected, we can use a complementary protecting group. So a good one to use in this case might be something like FMOC. So FMOC is actually quite bulky. You've seen the structure. If you had one equivalent of FMOC chloride and then one equivalent of BOC anhydride, then you'll get the FMOC going onto that terminal nitrogen off the side chain, and then the BOC going on the other nitrogen. So what this means is that when you deprotect the amine group, when you're making peptides, this FMOC group will stay on. You could even do the reverse too. If you're using FMOC synthesis here and have BOC as your group here, that would also work. All right, so that concludes this section on coupling agents and peptide chemistry.